What about expanding the receptor repertoire? Is there any interest in expressing exogenous receptors, like, I don't know, gunpowder receptor or whatever it is that the military is interested in? Is that have there been examples of dropping in engineered receptors into the olfactory system?
There have been early on also in demonstrating that any sort of G protein coupled receptors, these sort of general class of receptors called, can actually be used to instruct formation of glomeruli. I don't think in a mouse there has been much drive so far to put in different receptors in order to detect new things, simply because the repertoire of 1,000 receptors is already capable of detecting a very large fraction of all chemical volatiles.
I give you one interesting example, and that's the work has been done recently in collaboration with Tom Boza lab. He take one specific receptor and overexpress it significantly. Kind of the number of glomeruli instead of 2 on the same olfactory bulb was 80. And he measured the behavioral threshold to that specific ligand. This is most sensitive. Behavioral threshold didn't change. Adding more glomeruli doesn't make you more sensitive. It's kind of counterintuitive, but that means that our olfactory system is actually so well debugged and working at its best performance, so it's very hard to improve it.
Unfortunately, I can't smell carbon monoxide. I wish I had a receptor for carbon monoxide, especially now that everyone's houses are shutting down and we're heating our houses by the fireplace. Odor space doesn't encompass every molecule.
I mean, you're right. I think it's well possible that for certain things that indeed do not carry any smell. On the other hand, I think it will be a stretch at this point to think of many molecules that are beyond the detectability of a mouse olfactory receptor repertoire. So if you think of BCIs for mouse olfaction in order to detect specific patterns of volatile chemicals that might be associated with specific disease or a specific explosive or something, my sense at this point would be that all these carry enough information across these repertoire of 1,000 existing receptors that the challenge will not be engineering a new receptor to plug it in and allow for detection, but actually to stably and robustly acquire the data along the spirit of what Gabe and Dima are working on in order to then robustly decode information from that. But it's certainly well conceivable, like the examples that Dima gave. I mean, I think for the last 25 years, people have been working on engineering specific receptors in the mouse, moving glomeruli a little bit, replacing receptors, studying the difference in point mutations in receptors. That is a relatively tangible challenge to then replace individual receptors, create new glomeruli, so create new receptors. So if one had a good reason, that would probably be a relatively simple problem compared to some others.
There was a paper out not too long ago, the McGann paper, and he was talking about some of the specific anosmias. Carbon monoxide is one. Oxygen you can't smell, of course. As Andreas mentioned, there's very few of these that are molecules that are bigger than 1 or 2 atoms. Once you start crossing that threshold of 2 atoms, there's usually a receptor that's capable of picking it up, and the olfactory system is capable of recognizing it.
But certainly, the flip side of the fact that mammals, let's talk about mice again, that mice can detect almost any volatile is that it makes behavioral experiments with these little chaps extremely challenging. You really have to think of all the possible controls to make sure that they're not able to detect whatever spurious odor there might be. Remember, I think one of my first extensive behavioral experiments, I worked through the night to learn that a mouse that I was training, it could smell whether I had touched a tubing from the outside or not. So the subtle differences of having touched one tubing and not the other was something the animal readily learned within a few tens of minutes. So you always need to really make sure you do the right kind of controls. The great thing about that notion is, of course, that any set of volatile chemicals that differs from any other set of volatile chemicals, for example, a cancer of one sort, or cancer of a different sort, and the breath of people, in principle, that difference in smells the difference, if there is a difference in those volatile chemicals, as there will be for many of those diseases, that's something that mice should be able to learn to detect, or even more simply, if you're able to record directly, you should be able to decode reliably. So I think that's quite really an exciting perspective.